Hello and welcome to Study Room. I hope you all are doing very well and studying great. In this lesson, we'll be learning Chapter 2 of Grade 9 Science that deals with chemistry. The name of the chapter is Matter Around Us Pure. Now, in the previous chapter, we learned about matter, we learned about the different states of matter, we learned about the physical properties of matter, we learned about the transition of one kind of matter to another, and many more things. In this chapter, we'll be learning about what is the purity of the matter around us, what determines the purity, what is the difference between an element and a compound, what is a mixture, what are the different types of mixture, what and how can you obtain the different components of a certain mixture, and so on and so forth. Now, let's study and see what this chapter has to offer. Types of matter in our surroundings. So there are two types of matter around us. One is pure and the other is a mixture. By pure, we mean that any element, for example, here we have taken gold. So in gold, you don't have molecules, you don't have atoms or molecules of any other component. Say in a gold molecule, in a gold compound, you don't have the molecules of the different types of toppings we have on pizza or on the different medicines, right? Gold, a tablet of gold, or any other substance which is pure, okay? In that substance, we only have atoms and molecules of that particular substance. So when you're taking a pure tablet of gold, you'll be only having atoms and molecules of gold. There will be no other atoms and molecules of other elements. What is a mixture? Mixture is mixture is basically a mix of two or more components, and majority the two or more components, they are the pure substances. So in medicine or in a pizza or for example sand, in any mixture there is a mix, there is a combination of two or more than two compounds. Those compounds may be pure, those compounds may be mixture as well. Okay, so there are basically two types of matter around us. One is pure and the other is a mixture. Is milk a pure or impure mixture? Now, when you see, the glass of milk or the tumbler of milk that you have in your home, you may consider that this is pure substance, right? But, but for a scientist, all these things are actually mixtures of different substances, and hence they are not pure. So, you may think that pure means having no adulteration, all right? But actually, what is pure and what is mixture? It basically depends on the amount of components, on the amount of substances that are there in that particular thing, all right? So, for example, milk. You cannot say that milk is a pure substance. Why? Because milk is a mixture. It has two or more components mixed in certain properties, all right? It has a combination of these properties. These components are water, fat, proteins, and they may be any other. So, for example, if you have sugar while you have milk, right? So, basically, you are dissolving that sugar in that milk. So, that milk already has water, that milk already has fat, and a certain amount of proteins and other nutrients, all right? But you're also adding sugar, or, if you have Bonvita, Horlicks, different flavor that you want to add to your milk. All these are basically dissolving one mixture. So you cannot call milk a pure substance. What do you mean by a pure substance? Now, I have been rambling about a pure and a mixture. So what are these pure substances? Let's find out. In pure substances, all the constituent particles are the same in the chemical nature. A pure substance consists of a single type of particles. In other words, a substance is a pure single form of matter. Now, for example, that the first slide that had gold, right? So, I told you that a tablet of pure gold, when you're taking a tablet of pure gold, you will be only having atoms and molecules of gold in it, all right? So, all the constituent particles in a tablet of a pure gold are the same in their chemical nature. All the atoms, all the molecules will perform the same, will have the same physical property, will have the same chemical properties. So a pure substance is basically those types of substances that consist of only a single type of particles. So they may be, they may look huge to you. For example, a diamond, or, maybe a glass of water, or a tablet of gold. So they may look very big to us, but the kind of particles that they have inside them, all of them are same. All of them have the same chemical nature. So in other words, we can say that a substance is a pure single form of matter. You only have one single type of atoms or molecules aligned, and all those atoms and molecules, they have the same functions. These particles, they are the pure substances. Now, what is a mixture? Okay, so mixtures are constituted by more than one kind of pure form of matter. Most of the matter around us exists as mixtures of two or more pure components, for example, seawater, minerals, soil, etc. So, like I told you that for example, a glass of milk, or the example of sand that I had given you earlier. Now, you may be wondering why sand. So, when you look at sand, all have those grainy, components. So, you may say that why is sand a mixture? But if you were to determine the kind of components, the kind of particles that sand is made up of, all those will have definitely there is silicon, all right, but there are other particles than silicon present in sand as well. So you have all these particles existing in a state that may look homogeneous to you, but actually they have very distinct chemical properties, all right. For example, juice. Now you may think that a glass of juice looks very, pure to you, all right, because all these substances, you may think that they have very similar connotation. But when you were to determine, if you were to determine the components that a juice is made up of, for example, if you have a mixed fruit juice or even a pineapple juice, you are adding water to that. That is not just the pulp of pineapple that you're getting. All the mixed fruit juices, they are combined in different proportions, right? So most of the matter that exists around us, they basically exist in the state of mixture. Why? Because it is actually very difficult to obtain a substance which is in its pure state. It's very difficult to obtain a form of matter which is in its pure state, because everything around us, they are basically reacting with one form or the other. So air, you have different gases present in the air, then there is water, then there are so many things, and all these types of particles, all these types of matter, they are in a constant flux with each other, they are in a constant reaction with each other, and because of that, it is difficult for us to obtain pure substances. So most of the matter around us, they exist as a mixture, and they exist as a mixture of two or more pure components, all right. For example, seawater, also you have in seawater you have water and a lot of salt and a lot of other particles added up, minerals, soil, all of these are mixture. How can you identify between pure substances and mixture? Now, I have given you the basic, guideline of how can you designate whether a substance is pure, whether a substance is a mixture. But then how do you identify? So, let's have a look. Dissolved sodium chloride can be separated from water by the physical process of evaporation. However, sodium chloride is itself a pure substance, and that cannot be separated by physical process into chemical constituents. Similarly, sugar is a substance which contains only one kind of pure matter, and its composition is the same throughout. So if you were to have a look at salted water, right, dissolved sodium chloride into water. So this is your basically a salt solution. So you can get you can get water and salt from this salt solution, but from this salt, from one grain of salt, or for example from one grain of sugar, it will be difficult to break, because these chemicals these substances, they are basically bonded by chemical bonds, all right. So sodium and chloride, they do not just sodium and chloride, they come together by some process of chemical reaction. They're going through a chemical change. So this bond that we have between, say, a molecule of sodium, molecule of chloride, between hydrogen, oxygen, and different substances, all right, they are difficult to break through, and you can only break them through by some process that is not very obvious physical in nature, all right. So you can sodium chloride can be separated from water, salt can be separated from water, but then again they themselves consists of some particles that are pure in state, and therefore its composition is the same throughout. Types of mixtures. Depending upon the nature of the components that form a mixture, we can have different types of mixtures. Alright, so we have a lot of pure substances or impure substances, and the kind of mix that you get, the kind of combination that you get, they can vary and they can differ. What are homogeneous mixture and heterogeneous mixture? So basically, mixture, they are of two categories, broadly speaking. Okay, one is the homogeneous mixture and the other one is a heterogeneous mixture. Homogeneous mixture is a mixture throughout the solution in which the composition is uniform. The main thing to remember in a form of homogeneous mixture is that the composition is uniform. It means the kind of constituents, the kind of particles that form a homogeneous mixture, they give the resultant product. They give the resultant product a very uniform kind of texture, very uniform set of properties. All right, it is very stable in nature. All right, a homogeneous mixture is very stable in nature, whereas a heterogeneous mixture is a type of mixture that allows the components to be seen as two or more phases are present. So the uniformity that you were seeing in a homogeneous mixture, you will not be seeing them in a heterogeneous mixture. So for example, if you take sand and water, so you know that sand and water, they cannot be mixed together, right? You can see two distinct layers of water and sand. All right, so you know that when you see a mixture of sand and water, they are not uniform in nature, they don't have any stability, and they don't have that very uniform, very cohesive sort of texture to it. Okay, that physical property itself is not present, that physical sameness, a very uniformity is not there. So that is a heterogeneous mixture. Whereas in homogeneous mixture, when you dissolve, say, salt or sugar into water and you mix them with a steel rod or with a spoon or whatever, so you get a solution. You get a solution that has, neither change its level. Sugar dissolved in salt. You cannot even see them with your naked eye. You cannot see the components, the different molecules of salt or sugar that have gone in between the constituent particles of water, if you may remember that particular activity from the previous lesson, right? So a homogeneous mixture has uniformity, a homogeneous mixture has stability, whereas a heterogeneous mixture has neither of these qualities. Let's have an activity to demonstrate between a homogeneous and a heterogeneous mixture. Now let us take four people, A, B, C and D. A takes a beaker containing 50 milliliter of water and one spatula full of copper sulfate powder. B takes 50 milliliter of water and two spatula full of copper sulfate powder in a beaker. And C and D can take different amounts of copper sulfate and potassium permanganate and mix the given components to form a mixture. So what we are having here is one of the person, they have taken 50 milliliter of beaker and they have taken one spatula, one spoon, whatever, full of copper sulfate powder, and they have mixed that copper sulfate powder into the 50 milliliter of water. So you know that when copper sulfate powder is dissolved into water, we get a blue mixture. All right, so that person A, they get a blue mixture. Okay, person B, they have also taken water and copper sulfate powder, but the quantity is almost double. They have taken two spatula full of copper sulfate powder. So the blue color, the intensity of the blue hue in this beaker of person B, it is more than what person A had, right? Because the amount of copper sulfate powder is more here. Whereas person C and D, they have taken different amounts of copper sulfate and potassium permanganate. So there is no water in what people C and D have taken. They have only taken different amounts of copper sulfate powder and potassium permanganate powder, so that blue and pink powdery substance, and they have mixed the components to form a mixture. So what C and D would be getting is sort of this thing that you can see in the diagram. what we observe here is that A and B have obtained a mixture which has a uniform composition throughout, right? Although the blue color, the difference is there in the intensity of the blue color, but the solution is uniform. You cannot distinguish between the particles of copper sulfate from the particles of water with your naked eye. There is a uniformity, there is a stability in a mixture. But in what C and D have, you can easily determine that, oh, the blue particles, they must be copper sulfate. Oh, the pink particles, they must be potassium permanganate, right? So they have different, level of stability, and they have different level of visibility that is perceived by a naked eye. So though both have obtained copper sulfate solution, this is for person A and B, the intensity of color of the solution is different. And C and D have obtained mixtures which contain physically distinct parts, like I told you, and have non-uniform composition. So the conclusion is that mixtures A and B have got a what are called homogeneous mixtures, or because the pattern is uniform, right? It is stable. So we can also say that homogeneous mixtures, they are solutions, okay? So homogeneous mixtures can also be equated, can also be said to be equivalent to solution, okay? And a homogeneous mixture can have a variable composition. Why they can have a variable composition? Because the level of copper, the amount of copper sulfate solution that was added to the beaker of person A was less than that of the beaker of person B. So we know that a variable composition can be obtained. And mixtures C and D, they are heterogeneous mixtures. Let's demonstrate another activity, how to distinguish between different types of mixtures. So let us take again 4 person A, B, C and D. Distribute the following samples to each person. Few crystals of copper sulfate to A, 1 spatula full of copper sulfate to B, chalk powder to C, few drops of milk to D. Each person should add the given sample in water and stir properly using a glass rod. Direct a beam of light from a torch through the beaker containing the mixture and observe from the front. Leave the mixtures undisturbed for a few minutes, filter the mixture. In this experiment, we are again taking, a beaker, and in that beaker we have, some amount of water in there. So we have taken a few crystals of copper sulfate and we have given them to person A, okay. Then we have taken 1 spatula full. So again, the quantity of copper sulfate to what we have given in to person B, that is more than what we had given to person A. Then we have given chalk powder to person C. So person C has chalk. It has a person C's beaker or whatever the utensil is that has a chalky consistency, and then we have only added few drops of milk D to the water of person to the beaker of what person D has. The beaker has water. So now each person should add the given sample in water and stir using a glass rod. Now to demonstrate what further properties the mixture hold, we are basically we are placing the beaker or the test tube in, say, a table, all right, and we are with the help of a torch, we are basically passing them through light, okay. So with the amount of different kinds of mixture that we have gotten, there will be difference in the level of there will be difference in how the light passes through the beakers of person A, B, C and D. What is the difference? The difference is the A, B and D, they got clear solution. So the copper sulfate, both the copper sulfate solution and the milk, they had got clear solution, while the chalky solution, person C, got suspended particles. Why suspended particles? Because the mixture, because the small components that chalk formed in water, they were not very easily dissolved. They did not get that uniform mix that, say, copper sulfate solution got, right? Path of light is visible for C and D. So the path of light, when you, as you can see in this animation, the path of light that we are, making the beakers fall through a torch, that torch light passes through beaker C and D very visibly. That is, for the chalky solution and for the milk solution, the light is passing through, and the mixtures are sorry, the path of light is visible through the beaker C and D. Mixtures are stable for A and B, that is both for both the copper sulfate solution. Mixtures are stable because we had already demonstrated in the previous experiment that copper sulfate solution is a homogeneous mixture. But what about D and C? So, but for C, particles begin to settle after some time. Now, even though we know that milk is not a pure substance, milk is a mixture, but when we added a few drops of milk to water, we observed that the mixture appeared to be stable. Okay, whereas the chalky particles in the C, for the person which had the C chalky mixture, that person observed that particles begin to settle after some time. So the chalky constituents that are there in the water, they go and settle down at the bottom of the beaker, and this process you may be familiar with. This is precipitation. So A and B have got a solution, C has got a suspension. Why? Because the chalk particles are suspended. They are there, either kind of hanging in between the water mixture. So for example, if this is the tumbler of what person C had, all right, so even the mixture appears to be white and very uniform, but actually if you see that beaker very closely, you may see that chalk particles are suspended. They are hanging in between the water molecules, and you may also see some particles that are settled at the bottom of the beaker. Whereas D, the milk solution, that is a colloidal solution. Now we'll be learning about a suspended particle and we'll be learning about a colloidal solution later in this chapter. For now, I hope that a homogeneous mixture, the difference between a homogeneous mixture and a heterogeneous mixture is clear. Question 1, what is meant by a substance? So substance is basically a kind of matter that has distinct physical and chemical properties. There is a uniformity in a substance, all right? The properties, they are very distinct, they are very particular and peculiar to that one form of substance. List the points of differences between homogeneous and heterogeneous mixtures. So like I told you before, that homogeneous mixture, they have very uniform quality, all right? They have a stability. So the basis of difference could be in the uniform sort of mixture that we obtain after we mix the components together. So there is uniformity in a homogeneous mixture. There is stability. The particles they are mixed in a very in a very easy manner. We cannot distinguish them between a naked eye, for example in a salt solution or in a sugar solution. So there is stability, right? And in a heterogeneous mixture, we do not have a stable product, we do not have a uniform product. So in a heterogeneous mixture, more often we can see the different kind of particles that are suspended in between each other. All right, next we'll be learning about what is a solution. Now, a solution is a homogeneous mixture of two or more substances. Examples of solution: lemonade, soda water. There are also solid solutions like alloys, and there are also gaseous solutions, for example air. So a homogeneous mixture, a uniform mixture, and a stable mixture of two or more substances, they are known as solution. Previously I had told you that homogeneous mixture could be equivalent to what a solution is. Now a solution does not only depend on the liquid, like solution does not only depend on water. Yes, there are lemonade, soda water, other sorts of solution, but the important thing to remember here is that there are also solid solutions and there are also gaseous solutions. For example, air is a homogeneous mixture, and solid solutions that we'll be learning about ahead, alloys, they are also solutions. In a solution, there is homogeneity at the practice level. So there is homogeneity. What do we mean by homogeneity? We mean that there is a certain sort of stability, all right, and there is a certain sort of uniformity. All of these characters are distinct. All of these characteristics are distinct, and all of these characteristics are visible in a solution. For example, lemonade tastes the same throughout. This shows that particles of sugar or salt are evenly distributed in the solution. Now, what we mean by the uniformity here is that if you take a sip of lemonade, all right, first sip of lemonade, what taste you'll be having at the first sip of lemonade will be the same taste that you'll be observing at the last sip of. So we do not observe a very sharp taste of the lemon, or a very neutral taste of water. That taste is not one after the other. Taste is a very uniform, very balanced mixture of salt and water, or of sugar and water together, if we are talking about a sugar solution, right? So this is what we mean by a solution. What are alloys? Like I told you, solid solutions, they are alloys. Alloy is a mixture of two or more metals, or a metal and a non-metal, and cannot be separated into their components by physical methods. But still, an alloy is considered as a mixture because it shows the properties of its constituents and can have variable composition. Now, there was a line here that solid solutions are alloys, but if we are to distinguish the physical and chemical properties, if we are to go through by that method, then alloys, they are commonly mixtures. They are not pure substances. All right, they do have some distinct qualities. They do have some distinct properties, but they are not solutions. They are mixtures when the characteristics are observed. And why are they mixtures? They are mixtures because their distinct components, that cannot be separated by physical methods. An alloy is considered as a mixture because it shows the properties of its constituents and can have variable composition. Variable composition means that they can exist in variable amounts. Say in one sort of alloy mixture, if there are two types of particles, A and B, so A can be more in one, B can be more in the other, and like that. The other more important reason why alloy is called a mixture is because it shows the properties of its constituents. So like if we have to say about brass, so the brass will also show the properties of zinc, and it will also show the properties of copper. So brass is a mixture of approximately 30% zinc and 70% copper, but it is a mixture, it is an alloy. This brass particle, it may show the properties of its constituent particles, that are zinc and copper. Water solute and solvent. In a solution, the two very important determinants are solute and the solvent. The very classic example is the sugar solution, or the salt solution. So basically you are adding sugar to water. Okay, so sugar is your solute, the constituent particles that you are adding to water. So water, since sugar is being added to water, water is your solvent. And a very important, I think you may be knowing this property, that water is a universal solvent, right? So water could be taken as a solvent, as a substance in which other particles can be dissolved into. All right. So solvent, the component of the solution that dissolves the other component in it, and usually the component present in the larger amount. Now, because it is dissolving, because water, for example, because water is dissolving something in it, so it should be present in larger amount. So the amount of solvent in a particular solution, it is always large than the amount of solute. Why? Because the solute is to be dissolved in a solvent. All right. So the solvent should hold. It should have that quantity that could hold that amount of solute. And solute is the component of the solution that is dissolved in a solvent and is usually present in lesser quantity. And you can see here in this diagram as well that you're adding solute to the solvent to obtain a solution. Examples to understand solute and solvent. Aerated drinks like soda water, etc. are gas and liquid solutions. So what you drink, your Pepsi, your Coca-Cola, or your basic soda water, they are basically gas dissolved into the liquid solvent. And the gases that they contain are carbon dioxide as solute, and water, the universal solvent, as the solvent. Examples to understand solute and solvent. Another example is air. Now, air is a mixture of gas and gas. So, what we had observed earlier was basically a solid, or solid or gas in water, right? So here we have gas in gas solution. So we saw that solid and liquid solvent, all right? So basically solid solute and a liquid solvent, and we saw in the soda water the gaseous solute in the liquid solvent. Now air is basically gaseous solute and gaseous solvent. Air is a homogeneous mixture of a number of gases, and its two main constituents are oxygen. Oxygen is present in the air 21% approximately, and nitrogen is present 78%. There are other particles as well, there are the gases as well, but they are present in very small quantities. Hence, nitrogen is considered as the solvent because it is present in a very huge amount, 78%, and while oxygen and the other gases, they are the solute. But you can say that oxygen is one of the main solutes. Examples to understand solute and solvent. The other example is of iodine and alcohol, which is known as the tincture of iodine. It is a very important, exam point of view question, that a solution of iodine in alcohol is known as tincture of iodine, where iodine is a solid and that solid is acting as the solute and the alcohol is the liquid solvent. Alright, so what we get, the mixture is known as tincture of iodine. Properties of a solution. We saw the examples, now let's have a look at the properties. So solution is a homogeneous mixture, yes, that is stated. The particles of a solution are smaller than 1 nanometer, okay, in diameter. So they cannot be seen by the naked eye. Like I have been telling you that it is also uniformly in the solvent. The solute is also uniformly in the solvent, that you cannot determine the quantity, the constituent particles of the solvent. So what you get when you add the solute into the solvent, what you get as a solution, now that solution has some other properties of its own, right? So that solution exhibits a very stable property, a very uniform quality, and you cannot observe that those particles by your naked eye. Now because of very small particle size, they do not scatter a beam of light passing through the solution. So the path of light is not visible in a solution. So what we see here is if you're adding say salt to water, alright, so because the salt particles, they get dissolved so uniformly in water that when you pass light through it, okay, so the light is not scattered. Why is not scattered? Because to scatter light, when light is passing through an object, that object is supposed to reflect light, right? So if there is no object over here that is supposed to reflect light, then how can light be scattered? Because the particles, because the solute, there is also uniformly in the solvent in a homogeneous mixture, that light is not passing, light is passing through, light is not scattering, alright. So the path of light is not visible in a solution. The solute particles cannot be separated from the mixture by the process of filtration. Why? Because they are dissolved uniformly. The atoms, molecules again in between the atoms or molecules of the solvent. So that cannot be dissolved. That cannot be separated from the physical process of filtration. Filtration is basically a physical process. You're not causing a chemical reaction to occur in that solution. So physical processes such as filtration cannot be used to separate particles from the mixture. The solute particles do not settle down when left undisturbed, that is, a solution is stable. Also from the basic precipitation process also, you cannot obtain the solute from the solvent. Concentration of a solution. The concentration of a solution is the amount, mass or volume of solute present in a given amount, mass or volume of solution. In a solution, the relative proportion of the solute and solvent can be varied. Now we have observed this, right? When we are doing that copper sulfate experiment, you may have noticed that the amount of solute and the solvent, that can be varied, right? So the composition can be varied depending upon the amount of solute present in a solution. It can be called dilute, concentrated, or a saturated solution. Dilute and concentrated are comparative terms. Okay, what do we see here? Let's have a look at the diagram. Dilute solution, concentrated solution, less amount of solute and a more amount of solvent, and more amount of solute and a less amount of solvent. What we mean by dilute solution? we mean by dilute solution is that the amount of solvent in a dilute solution is more than the amount of solute. Okay, and what we see in a concentrated solution, we see in the concentrated solution is that the amount of solute present in a concentrated solution is more than the amount of solvent. Okay, so we know that solute or solvent, the properties of the the quantities of solute and solvent, they can vary, the composition can vary. So when you are taking a lot of solvent, a large quantity of solvent, and when you are adding a very few amount of solute, so you're basically, that solution is a dilute solution because the solvent is more than the solute. But when you are taking a very less quantity of solvent, and when you're adding a large quantity of solute to the solvent, you're basically making a concentrated solution. So the amount of solute, when it is more than the amount of solvent, we get a concentrated solution. So dilute and concentrated, they are basically comparative terms. What about saturated solution? We'll be learning about it, later on as well. But for here, you can understand saturated solution as a solution. Now, a particular amount of solvent, right? It can hold only a particular amount of solute at a specific temperature. So, at a specific temperature, the maximum, when a fixed quantity of solvent, it dissolves a fixed quantity of solute, and when that solute is maximum in its proportion, all right, then we get a saturated solution. So depending upon the amount of solute present in a solution, we can have dilute, concentrated, or a saturated solution. And a concentration of the solution is always the amount, and that amount can be either expressed by mass or by volume. And we have to compare it also to mass and volume of the solution. Activity. Is solubility of substances same in particular solvent? Now take approximately 50 milliliter of water, each in two separate beakers. Add salt in one beaker and sugar or barium chloride in the second beaker. With continuous stir, when no more solute can be dissolved, heat the contents of the beaker to raise the temperature by about 5 degrees Celsius. Start adding the solute again. Now we have taken, the amount of solvent is fixed here, right? We have taken 50 milliliter of water in both the beakers. In one we have added salt or sugar, and the other we have added barium chloride. What we are doing it, we are adding and then we are stirring. So when we see that, when no matter how much more salt or no matter how much more barium chloride we add, it is not able to dissolve into water, we heat the contents. We heat the contents so that the intermolecular space increases, right? And with the increase of the intermolecular space, more particles of salt or more particles of barium chloride may get the opportunity to be dissolved. All right, so we raise the temperature by about 5 degrees Celsius, and then we start adding the solute again. What we observe is that amounts of salt and sugar dissolved in different beakers are different. All right, this experiment, since we had taken a very fixed amount of solvent, right, we had only taken 50 milliliter of water, but we observe that by adding different solute to a fixed quantity of solvent, all right, is different. The different substances in a given solvent have different solubilities at the same temperature. Since we were also increasing the pressure only by 5 degrees Celsius, all right, and the amount of solvent was also fixed. So the only thing varying was the amount of solute, and from this we can conclude that different substances in a given solvent, they have the different solubility at the same temperature. Saturated versus unsaturated solution. When no more solute can be dissolved in a solution at a given temperature, it is called a saturated solution. And if the amount of solute contained in a solution is less than the saturated level, then it is called an unsaturated solution. So it's a very basic thing to understand. Now a particular, since you are taking a fixed amount of solvent, right? So a particular solvent can only hold a particular amount of solute. So after, no matter how much you have increased the temperature or decreased the temperature, There will come a time when no more solute will be able to dissolve in a solvent, when no more salt or sugar or barium chloride will be able to dissolve in water. So when that state of the solution is reached, when no more solute can be dissolved in a solution, at a given temperature, this is very important, at a given temperature, it is called a saturated solution. And then we observe that we can increase the temperature and add more solute to it, or we can, or the temperature may be the same, but we can still add more solute to it. So we, from that we can determine that yes, the solution is unsaturated and the saturation level of that particular solution has not yet reached. So unsaturated solution, we can add more solute and we can dissolve the solute into the solvent, all right. And when a saturated level is reached, what will happen? No more solute will be able to be dissolved. So what happened in a supersaturated solution? Now, suppose the solution has reached its level of saturation. You are seeing that the solute here, the solute is here. So you can see that no matter how much you are stirring the solution or you're raising the temperature, the solute is not able to dissolve in the solution. We know that we have reached a saturated solution, but still if you keep adding, all right, if you keep adding to that, if you keep adding the solute to that solution, we have been reached to a super saturated solution, and in that state, the unstability of the solution. Now the solution, since you're adding solute to the solvent, so you're basically making the solution unstable. You're making a stable solution unstable, and that instability, it causes crystals to form. And you can see this phenomenon happening especially if you lower the temperature. If you lower the temperature, what will happen? You will be basically decreasing the amount of space between the molecules of water, all right. So when the amount of space is decreased, obviously the amount of solvent that were dissolved earlier would come out, right? They would come out of that state, and you will observe crystals. That instability in a supersaturated solution causes crystals to be formed. What is solubility? The amount of the solute present in the saturated solution at this temperature is called its solubility. So the amount of solute, a particular amount of solute present in a saturated solution at this temperature, at a particular given temperature, is called its solubility. Formulas for expressing concentrations. We have three formulas to express concentrations. Let's have a look. Mass by mass percentage of a solution means you're taking mass of the solute and you are dividing it. Mass by mass means you are dividing it by the mass of the solution, and because you have to obtain a percentage, so you're multiplying it by 100. Mass by volume means you're taking the mass of the solute and you are the mass or the volume of the solute would always be divided by the mass or the volume of the solution, because obviously you have to check for the concentration, and what will determine the concentration? The solute and the solution, right? So mass by mass percentage is there, where you are taking mass of the solute divided by mass of the solution, and then you're multiplying it by 100. Then there is the mass by volume percentage, where you are taking mass of the solute, okay, and you are dividing it by the volume of the solution, all right. And then again, because you have to obtain a percentage, so you are multiplying it by 100. And there is the volume by volume percentage. So you are taking volume of solute, you're dividing it by the volume of the solution, and then you're multiplying it by 100. Let's have a look at the illustration. A solution contains 40 grams of common salt in 320 grams of water. So we know that the common salt is the solute. So the amount of solute is 40 grams and the amount of solvent, that is water, is 320 grams. Calculate the concentration in terms of mass by mass percentage of the solution. Now this is a very easy question, right? Why? Because we only have to calculate the mass by mass percentage. So we know that a concentration is always determined with respect to the solution, right? We take the solute in respect to the solution. So we know that mass of the solute is 40 grams because that is the basic information that is given to us in the question. And we also know that the mass of the solvent is 320 grams. we only have to determine mass of the solution now. What is solution now? A solution is made up of solute and solvent. So if we were to calculate the mass of the solution, we will definitely be adding up mass of the solute, that is 40 grams, and mass of the solvent, that is 320 grams, and we will be getting 360 grams. That is the mass of the solution. Now it's an easy step ahead. We only have to calculate the mass percentage of the solution. For this, we will be taking mass of the solute and we will be dividing it by mass of the solution. So that is, we will be taking this 40 gram, that is the mass of the solute, and we will be dividing it by this sum that we obtained here, 360 gram. Okay, and then we will be multiplying it by 100 to get our result. That is and that will be the concentration in terms of mass by mass percentage of the solution.